The next thing we can do then is to group the tasks we have just defined into simple task networks. And such a task network is really just an acyclic directed graph. And this graph consists of some nodes denoted by the set U and some edges given by the set E. And the nodes in a task network are simply a set of tasks, T1 through Tn, where each of the elements in the set T1 through Tn is a task. So it's a syntactic expression of the form given a task symbol and some arguments, not just a task symbol. And then we have the edges in the task network, which simply define a partial ordering of those tasks in the set U. And in what follows, I will use the same notation we've seen previously, so I can say that a task Ti comes before a task Tj by using this symbol. And that's it. That's a task network consisting of a set of tasks and a set of edges that form an acyclic directed graph. Note that the graph has to be acyclic. And task networks, like tasks, can be ground or primitive, or both. And a task network is considered to be ground if all the tasks in it are ground, not just one, but all of them. And it's considered primitive if all the tasks in the network are primitive. And it's ground and primitive if both properties hold for all the tasks in the network. But if only one task in the network is unground, then we consider the whole network unground. And if only one task in the network is non-primitive, then we will say that the whole network is non-primitive. Apart from being ground and or primitive, a task network can also be totally ordered or partially ordered. To define the ordering in a task network, we say that Tu comes before Tv in the network W consisting of nodes U and edges E if there is a path from Tu to Tv. Then we can say that our simple task network W is totally ordered if the set of edges in this network defines a total order on our nodes. And a total order here means that every node is ordered with respect to every other node by this network. So there are no two nodes in this network that are not ordered with respect to each other. And if this is the case, then we can take our network W and simply represent it as a sequence of tasks, written like this here, just like we've written a sequence of actions earlier. This is a sequence of tasks starting with Tn and ending in T1, which are all totally ordered with respect to each other. So this gives us a third property that a task network might have. A task network can be totally ordered, ground, and primitive. And if we are given such a network described by the sequence T1 through Tn, then we can define the plan that accomplishes this task network by this function pi of w, and it is simply defined as the sequence of actions a1 through an, so it's the same length in the sequence, where each ai is the same as the ti. So the name is the same as the name of the task. In other words, each action accomplishes the task that is at the same position in the sequence of tasks in the task network. And to make sure you understood all this correctly, here are a few examples from our DocWorker robot domain as an STN domain. The first we have given here is a set of tasks, and the first task is T1, described by taking with crane at location container 1 from container 2 in pile 1. This task is primitive. It is primitive because we have an operator that has the same name, namely take. And this task is ground because all the arguments that are given to this task are all objects and not variables. Similarly, we have a task T2, which consists of the same task symbol, take, and it takes with the crane at the same location, container 2 from container 3 in pile 1. And again, this task is primitive because we still have an operator with the same name, take, and it is ground because all the arguments are constants and not variables. And then we are given a third task here, T3, which is move stack P1 Q, And this task, of course, is non-primitive. It is non-primitive because move stack is not the name of an operator we've defined in the DocWorker robot domain, and is unground because q here is a variable. We're not specifying the stack to which we're trying to move our containers. So given these three tasks, we can now form task networks. And the first network we have is W1, and it consists of all three tasks defined above, T1, 2, and 3. And it has two ordering constraints, namely T1 before T2 and T1 before T3. So this task network is partially ordered because T2 and T3 are not ordered with respect to each other. It is non-primitive because it does contain at least one non-primitive task, in this case T3, and it is unground because it also contains one unground task. Again, this is T3. And then we have a second example of a task network, W2. This consists only of the first two tasks, T1 and T2, and it has only one ordering constraint, T1 before T2. This network is totally ordered, and we can write it as a sequence T1, T2, because all the tasks are ordered with respect to each other. And then we can say that this network is ground, because again, all the tasks in it are ground. T1 and T2, these are the two tasks here, were ground and primitive. And again, since these are the only tasks we have here, this whole network is ground and primitive. So this is a totally ordered ground primitive task network, and that means we can immediately derive the plan that accomplishes this task network. And this is pi of W2, as defined earlier, simply consisting of the two actions that have the same name, the syntactic expression describing this action, as the two tasks in the task network. So now we know what tasks are, and we know how to form networks out of these tasks. And for some of these networks, we even know how to form plans that accomplish these task networks.